Thanks for attending my talk. Today I'm going to talk about our paper, Scalable Build Service System with Smart Scheduling Service. Here is the roadmap of my talk. First, I'm going to talk about motivations, then I'm going to talk about the system's requirements, background, architecture, scheduling service, experience, and finally the conclusion. Google has a monolithic code base with billions of lines of code. On average, each day, we have over 100,000 code submissions and triggers over 1 billion targets and runs over 15 million builds. Many of our surveys requires a scalable build service system. For example, our continuous integration service, our online IDE service, and our production release service, they all require a scalable build service that can run the build or test the change. Our build service system should have the following requirements. First, it needs to be scalable. The system should be able to handle hundreds of build requests per second and runs millions of builds per day. Second, it needs to have low latency. We don't want to slow down our developers' productivity, so the build service overhead should be small and reasonable. Third, it needs to be reliable. Since we have so many number of builds being running concurrently, we have a lot of machines. As the number of machines is large, machine failure is not a matter of if but when, so we need to be able to tolerate machine failures. Fourth, the builds should be prioritized. Some builds are more important than other builds. For example, a human-triggered build is often more important than an automation tool-triggered build. And last, the system should provide instant feedback. We want to provide a remote build service that behaves like the build is running on the developer's local machine. Before I dig into the system, I want to first introduce some background. These slides show some of the build targets. In Google, we use Bazel as our build tools. A target is declared as the following. You can have a Java library targets and declare the name of the target and also the source files. You can also have a Java binary targets that declares the names and the main class, which is the main entrance of the system. You can also declare a Java library for the test. And then finally, you can specify a Java test target that includes all the test classes and specify the size and the required executor type. A Bazel build command consists of the following. It must have a command name. It could be either build, test, coverage, or etc. Then it must specify the flags. For example, you can specify the number of concurrent jobs that can be used in the test or build. Finally, it needs to specify the build targets. Here we show a hello world targets. Put together, this is how a Bazel command looks like. A build could be in one of the three states in the build service system. It could be in the in-queued state, which means the build is in-queued to the system and waiting to be dequeued. It could be also in the in-progress state, which means the build is dequeued to a worker and is executing. Finally, it could be in the finished state, which means the build is finished and the result is available. A build could be one of the four priorities: emergency, interactive, automated, and batch, ordered from highest to the lowest. An emergency build is something like a build that is required for emergency production bug fixes. An interactive priority build could be a build that is required by the pre-submit service that blocks the code submissions. An automated build could be a build that is required by the post-submit service that runs the test at the given revision. A batch priority build could be a build that collects the code coverage. Our service is built on top of a Spanner database. The Spanner database offers the globally comparable transactions and many replicas, and it also has automatic load balancing and scale up to millions of machines and is able to store trillions of database rows. It is used to store the global state of the build request. This slide shows an example Spanner schema. For example, it declares a build table, which includes a unique build ID, the build state, the build itself, including the build command, and the build priority and the request time. The primary key of this table is the unique ID. You can also declare a secondary index that allows the spanner to order the build by the columns you specified. For example, in this case, we have an index called state priority request time, which will order the builds first by the state, and then by the priority, and finally by the request time. This slide shows the high-level components of the build service system. The client enqueues a build to the scheduling service. The scheduling service queries a machine learning service to predict the resource used by the build. Then it also persists the build state to the Spanner database. The scheduling service only dequeues a build to the Bazel worker if there is enough resource available. The code governor keeps track of the amount of available resource. The Bazel worker starts up a Bazel process to run the build. The process translates a build into executable actions and sends those actions to the executor cluster. The cluster runs the actions and reports back the result. It also reports to the code governor about the available resources. During the build execution, the Bazel worker sends build events to the build event service and reports the build progress. The client can listen to the build event service and query the progress of the build. The output storage system listens to all the builds through the build event service and provides an UI with build logs and status for the users to check or debug. The system provides the following client APIs. The create-build API enqueues a build to the system. The get-build API gets the build status of a build. The cancel-build API cancels a build. The watch-build API watches the progress of a build from the build event service while it's running. The scheduling service provides the create-build, get-build, and cancel-build APIs for the clients. It also provides the get-next-build, renew-lease, and finish-build APIs for the Bazel workers. Once the Bazel worker is idle, it will send a get-next-build request to the scheduling service asking a build for dequeue. While the Bazel worker is executing the build, it sends the renew-lease request to the scheduling service to let the scheduling service know that the worker is still alive. After the build is finished, the Bazel worker sends the finish build request along with the final build status to the scheduling service. Conceptually, all of the build in the scheduling service forms a priority queue. Priority queue is implemented as a spanner secondary index. The scheduling service needs to estimate build cost and throttle the build based on the available resources, and finally finds the best Bazel workers for incremental builds. The Bazel workers runs the Bazel process and executes the build. It controls the memory, the network, and the CPU usage of the Bazel process. We use a pull model that allows the Bazel workers to actively pull the builds from the scheduling service instead of the scheduling service push build to the Bazel worker. The Bazel worker needs to send the renew leases to the scheduling service. Finally, when the build is finished, the Bazel worker needs to report the build final status to the scheduling service. A Bazel process does the following things. It needs to do the dependency analysis. It also needs to translate the build into actions for execution. Finally, the Bazel worker needs to publish build event to the build event service. The executor cluster executes the actions provided by the Bazel workers. Internally, it has an action cache, and in practice, over 99% of the actions hit the cache, which means a lot of the work are reused. The executor cluster also provides different executor types. For example, it has its x86 CPUs, the Mac executors, the GPUs, TPUs, and etc. It needs to keep track of the occupied and idle executors and report them to the code governor. For the rest of the talk, we are going to use the Executor Service Unit, aka ESU, to unify both the executor and the memory cost. And we use that to measure the cost of the build. The code governor collects the executor resource quota from the executor cluster. So internally, it uses a PID controller to report the available executor resources to the scheduling service. A PID controller continuously calculates an error value as the difference between a desired set point and the measured process variable, and applies a correction based on proportional, integral, and derivative terms. The input to the process is the output from the PID controller, and it is called the manipulated variable. You can think of the PID controller as a cruise control when you are driving a car. The set point is the target speed you want to achieve. For example, if you want to achieve 100 miles per hour, the process variable is the current speed, and the manipulated variable is how hard you are going to press the accelerator. For our case, the set point is the total executor resource capacity. The process variable is the current used executor resource. The manipulated variable is the amount of executor resource that we should fill by executing more builds. The build event service provides the watch build client API. It keeps track of all the build events sent by the build service system or the Bazel process, and it provides a protocol to report the build progress and target result to the users. The build output storage service watches all the remote builds, and it stores the build output, for example, the logs, the status, or the statistics of the build. And finally, it provides an UI for the users to check the build status and debug failures. I want to talk a bit more about the build cost estimation in our scheduling service. We use a linear regression model to estimate the amount of resources a build would cost. We get the actual build cost from the executor cluster. The features are the build flags, targets, target count. We use an off-the-shelf black box optimization tool similar to AutoML to search for feature cross. The feature cross allows us to translate a nonlinear separable problem into a linear separable problem. I want to describe our build throttling algorithm in the scheduling service. The scheduling service receives the target amount of resource from the quota governor. It also knows the in-used resource from the spanner database. And before the service starts to decide which build can be dequeued, it first sets the reserved resource to 0. Then it scans through the build from the highest priority to the lowest priority and compare the target resource against the sum of the build cost, in-used resource, and the reserved resource. When the first build comes, the target resource is bigger than the sum, so the first build can be dequeued. Then we add the first build cost to the reserved resource and check the second build. Now the target resource is smaller than the sum, so the second build is throttled. This is similar for the third and the rest of the build. With the above algorithm, the scheduling service only dequeue builds if enough resource is available. It always dequeue high priority builds before low priority builds. It can also prevent low priority cheap build from starting high priority expensive build. The PID controller compensates for the build cost estimation errors. In case we overestimate build cost, the target resource would go up, which means we are gonna dequeue more builds. And in case of the underestimation of the build cost, the target resource will go down, which means we are gonna dequeue fewer builds. We have two worker selection algorithms. The first one is called the exact match algorithm, in which case we compute a hash of all the build flags and targets, and send the hash to the worker that dequeued the build. When the next build comes in, we are gonna find the worker with the same hash, and use that worker to dequeue the next build. The second algorithm is called the closest match algorithm, in which case we compute a set of hashes of all the build flags and target prefixes, and then we send the set of hashes to workers. And when the next build comes in, we find the worker with the overlapping hashes. Here I want to explain more details about the closest match algorithm. Suppose we have a command bazel test -- flags target T1 target T2. So for target T1, we compute a set of hashes H1, which includes the hash of the flag and the target T1, and the hash of the flag and the prefix of the target T1. Similarly, for target T2, we compute a set of hash H2, and we union H1 and H2 and set the union set to the worker. When the next command comes in, let's say the command is bazel test -- flag target T3 and target T4 with the same prefix as the target T1 and T2. Then for target T3, we compute a set of hash H3. For target T4, we compute a similar set of hash H4. We are gonna dequeue this new build to the worker that runs the first build, because we found both H3 and H4 has overlapping hashes with the hashes on the worker. Because we have tens of thousands concurrently running builds and a lot of workers, it is quite common that we can reuse the previous build result. This includes both the dependency analysis result and the action result. Now I want to talk about our production setup and some experience we have for our build service system. We collect the data between October 1st, 2019 and December 31st, 2019. During the time, we run 15 million builds on average and up to 25 million builds per day. Our services are deployed geographically over the world. The dequeuing service jobs, the bazel workers, and the executor clusters are deployed in the same data center to minimize the network latency. For the build cost estimation, we use the last 17 days of data to train our model. 95% of the data is used for training, and the rest 5% is used for testing. The table shows the average, minimum, median, and maximum queries per second per service API over the last 24 hours window in our experiment. It also shows the API availability. The average create build QPS over the last 24 hours ranges from 100 to 250. It reaches the minimum QPS at weekend and the maximum QPS at weekday peak hours. This is similar for all other services. The average QPS of getBuild ranges from hundreds to thousands. It is higher because the getBuild API is called multiple times to query the build status during the life of a build. Cancel build is not common in practice, so it has smaller QPS. The getNextBuild and FinishBuild API have a similar QPS compared to that of the CreateBuild API because each build typically involves each of these APIs only once. The WatchBuild QPS ranges from hundreds to thousands because multiple clients could watch the same build. Our services are available for more than 99% of the times when it is invoked. This table shows the average, minimum, median, and maximum latency in milliseconds per service API over the last 24 hours window in the experiment. The average CreateBuild latency ranges from 100 milliseconds to 3 seconds. We want to keep the latency low for better user experience. The average getBuild latency is a few milliseconds because it simply needs to read the spanner table to get the status and return it to the user. The average cancelBuild latency is around 100 milliseconds, and it is higher than the getBuild latency because it requires a spanner write and update build status. The average getNextBuild latency is around hundreds of seconds because often the build is throttled and the worker cannot get the build to work on soon. The average FinishBuild latency is around hundreds of milliseconds for a similar reason as the cancelBuild API. The average WatchBuild latency is tens of seconds because it involves a lot of build events and the client may need to wait until the build is finished before the API is finished. This table shows the statistics for each build priority. There are very few emergency builds and many builds are interactive or automated priority. Batch builds account for around 1% of our builds. The build size in kilobytes is correlated with the number of targets in each build, and lower priority builds tend to have more targets. This is expected because human triggers build like a code change often involves only a few affected targets. But tool-triggered builds like collecting the code coverage often involves a lot of targets. Higher priority builds stay shorter in the queue compared to low priority builds. For example, the emergency builds are instantly dequeued, whereas the batch builds often stay in the queue for an hour. The execution time of all builds are comparable, and low priority builds seems to take more time to execute. Now I want to talk about our build cost estimation and worker selection results. For x86 executors, we achieve an average absolute error of 5.7. For Mac executors, we have a slightly worse result, with an average absolute error around 8.1. For all other executor types, we achieve worse accuracies. This is because most of the builds use x86 executors and Mac executors, so we have more training data. And also, the executor cache makes prediction harder. For worker selection, we exclude builds that do not reuse analysis or action cache, because those builds cannot gain any benefits from the worker selection algorithm. We found that the worker selection algorithm can reduce the average execution time from 64 seconds to 55 seconds, which is around a 10% improvement. In conclusion, we demonstrate a build service system that runs tens of millions of builds per day and to support the industrial scale development. We also present the architecture of the build service system after years of refinements in Google. And finally, we provide the experience on the scalability and the efficiency of the build service system. And we hope our paper can inspire other researchers or practitioners who want to build a similar build service system. Now I'm open to take any questions you may have. Feel free to contact me for future collaboration. Thanks.